Thanks for introduction. I'm Hao Zhong from Shanghai Jiao Tong University. The title of my paper is Which Exception Shall We Slow? In this paper, we propose the first approach to predict which type of exceptions shall be slow when a type of error occurs. First of all, let me introduce the exception handling mechanism. Many program languages allow programmers to use exceptions to handle errors. For example, both Java and C++ support this feature. Let me introduce how it works with the below Java example. In this example, when a directory is null, the code throws an exception. The throw exception can be caught if the type of the throw exception matches the expected type in the catch statement. For simplicity, I put the throw statement directly inside the catch statement. In real code, the throw statement can be hidden in other methods. After the exception is caught, the error can be handled. The syntax of the C++ is different, but the procedure is similar. In other programming languages, we can also find similar mechanisms. Researchers have proposed various approaches to support catching and handling exceptions. For example, for catching exception, the FS paper analyzes which exception shall be catched. The ASE paper analyzes which code line shall catch exceptions. For handling exceptions, the face paper and the security paper analyze which methods shall called in catch statement. Furthermore, the scan paper recommends code examples so programmers can better write handling code. However, bugs in throw exceptions are rarely studied. Let me introduce a problem with a resource leak. Suppose that we have an acquire resource method and a release resource method. The two methods must be called in pair. If not, resources are not cleaned and it causes resource leaks. The do-something method throws an exception for type is T if it fails. If the do-something method goes smoothly, this example will not cause resource leaks. However, if do-something goes wrong, the release resource will be bypassed. The error will not be handled. As a result, it can cause resource leaks. The ASE paper predicts which code line catch exceptions. If it predicts that the do-something code line shall catch an exception, programmers can add the try statement as shown in the below code example. The catch statement needs to know which exceptions shall be caught. The FS paper can make this prediction. Even after the do-something method is put inside the try statement, its error is not handled. Programmers shall call some methods to clean the resources. The FS paper predicts which methods shall be called to clean the resource. It is sometimes difficult to write handling code. The scan paper can recommend useful code examples so programmers can write correct handling code. My question is that, what if a method does not throw the expected exception? In this example, the doOthers method throws a different type of exceptions. Its errors will not be handled. It can cause resource leaks. Can programmers throw wrong exceptions in real code? My answer is yes. This is a real bug from Cassandra. In this bug, when the disk is full, the disk filler police is not triggered. The above code shows how Cassandra implements the disk filler police. When the disk is full, the code catches FS write error. After the exception is caught, the write-set method shows the handling code. It implements the disk filler police. However, when the disk is full, the below buggy code throws another exception, long-time exception. As the throw exception is not as expected, the exception is not caught. As a result, the error is never handled. The disk filler police is not triggered. To fix this problem, programmers change the slowing exception from long-time exception to FS right angle. It is difficult for a new programmer to slow the correct exception. This correct exception is self-defined and it has no arguments. A new programmer may not even know this exception. In fact, by definition, it is also legal to slow long-time exception under this programming context. However, the local consensus of Cassandra is to slow the other exception, f as right angle. For this problem, our insight is to encode the local consensus into a model. The model can be automatically trained. The trained model can recommend correct exceptions to programmers. Based on this insight, we propose an approach called SEX. It uses J48 and AdaBoost as its classifier. The right table shows our extracted features. The features are extracted from the contexts of slowing exceptions. From each slowing exception, it extracts a labeled instance. The labeled instance allows us to train our model. The classifier is simple and classical. You can read our paper for details. Our tool has two application scenarios. The first is to assess programming. It is useful for programmers who are skillful but do not know the local consensus of slow exceptions. They can write all the code but do not know how to slow the right exception. For example, the programmer who writes the Cassandra bug may need our tool. For this scenario, the accuracy is important. To evaluate its accuracy, we built a large benchmark. The benchmark contains more than 10,000 instances of slowing exceptions. These exceptions were extracted from non-open source projects. As shown in RQ1, our tool achieves reasonably high F-score values on all the projects. Our data are imbalanced. We introduce MCC since it is a measure for imbalanced data. Our tool achieves high values also on this measure. In the second RQ, we evaluate the differences of predicting self-defined exceptions and those defined by libraries. In this figure, self denotes the exceptions defined by programmers, and lib denotes the exceptions defined by API libraries. Our results show that our tool achieves better results when it predicts self-defined exceptions. In the third RQ, we remove each feature to understand its importance. Although their impacts are still matter, we found that the scope, checked arguments, exception defined by method headers, and exception shown in other low code occasions have more visible impacts than other features. In RQ4, we evaluate how effective to learn from other projects. For example, for ASM, we use the data from all the other projects as the training data and the data from ASM as the testing data. We compare the F-score with those in RQ1. Our results show that when the training data come from other projects, F-score values are reduced to around 0.6. The second scenario is to detect bugs. In our benchmark, we consider the exception written by programmers as a golden standard. However, in the wild, no golden standard is fully correct. Can our tool predict exceptions that are better than the golden standard? We use three criteria to determine which one is better. First, we analyze which exceptions are slow under similar programming contexts. Here, we mainly consider the code structures. Second, we analyze which exceptions are slow by similar methods. Here, we mainly consider method names. Finally, we read the documents of exceptions to learn which one is better. Here, as we select the latest versions of the 9 projects, we have no idea whether they contain long-slow exceptions. To our surprise, We found better predictions in borderline projects. The result indicates that long-slow exceptions can be a relevant problem. We report our better predictions as bugs to the programmers. 13 bugs were already fixed. The feedback from programmers indicates that long-slow exceptions is an important problem. As a result, our target problem is important and relevant. Here is an example from Apache I/O. When the size is below 0, programmers throw illegal argument exception. Our tool predicts that it's just throw I/O exception. We believe that our result is better, since other code locations throw I/O exceptions when the size is illegal. Here is an example from PDF bugs. When the length of the bytes is 0, programmers throw illegal argument exception. Our tool predicts that it's just throw I/O exception. We also believe that our result is better, since other code locations throw this exception when bytes are illegal. Both bugs were fixed. The feedbacks from programmers are positive. The programmer from Apache I/O says that our bug report is interesting. The programmer from PDF bugs agrees that our prediction is better. Although our cross-project learning results are not quite positive, the two examples from two projects show a similar pattern to slow exceptions. Let me summarize my work. Programmers can throw long exceptions since they do not know the local consensus of slow exceptions. To handle the problem, we propose 6. It learns a classification model from slow exceptions written by programmers. 6 is accurate. It detects 20 bugs from the latest versions of 9 open source projects. Among them, 13 were already fixed. That's all for my presentation. If you have any questions, please contact me through my email. Thank you.